our next speaker, I'm happy to introduce Jesper Lützen, will be talking about impossibility and existence in the history of mathematics.
And of course, I want to start by thanking the organizers. June, listen. June, I'm thanking you. Thanking the organizers for organizing this wonderful conference on modern history of mathematics and for inviting me to give this talk here. So, not long ago, I published this book on the history of mathematical impossibility, and I thought it would be interesting to take some of the things in that book and talk about them here. Now, of course, I know this workshop is about modern history of mathematics, and the question is this modern at all? And I want to say, yes, it is in a certain sense, because at least it has attracted the interest of several authors over the last years, and I here flash some of the title pages of some of the books that deal with impossibility in science and mathematics. But I want also today to combine it with sort of the other side of the coin, namely the question of existence. Not that I'm going to give a sort of deeply metaphysical, ontological talk. I'm going to talk about impossibility and existence as it occurs in mathematical practice. Here it is. And I'm going to talk about mathematics as a problem-solving activity rather than a theorem-proving activity. Indeed, during the 4,000 years of history of mathematics, problem-solving has been the main activity over most of the time. And even for those parts of the history of mathematics and those places where we think of theorem proving as being the central activity of mathematics, it has often been pointed out that problems are in fact what gives the lifeblood of mathematics. This has been pointed out by Wilbur as far as the Greek mathematics is concerned, and by Hilbert as far as modern mathematics is concerned. So I'm going to look at mathematics as problem solving. Now, of course, when we have given a mathematical problem, we want a reaction, and of course the reaction that most of us want is to see a solution. Display a solution, of course, is the best way to react. But of course, there are cases where you can prove that a solution exists without necessarily being able to provide it through a construction or a calculation, so non-constructive existence proofs. But then, of course, there are also cases where you can, in fact, show that there is no solution. And that can be then interpreted either as a failure or as a kind of solution to the problem. And I'll come back to that later in the talk. Now, in real life, outside of mathematical departments, impossibilities are often thought of as challenges. I mean, just think of Alexander the Great, who untied the impossible Gordian knot. And if you look in different lists, there are lists on the internet about impossibilities. And the morale of all of them is something like, nothing is completely impossible, and the highest goal in life is to achieve the impossible. Let me just quote the first one up here. The impossible is what nobody can do until somebody does. Or Napoleon, who is supposedly should have said, impossible is a word to be found only in the dictionary of fools. Now, of course, we know that in mathematics it is that it is only fools who try to, say, trisect an angle using only ruler and compass. And the reason why only fools try to do the impossible in mathematics is that we try to phrase our impossibilities in a more precise way than is usually done in ordinary life. For example, in the question of trisection of an angle, we specify that this has to be done by ruler and compass, And we even specify what we are allowed to do with the ruler and compass. We are allowed to do exactly what Euclid postulates in the postulate 1 to 3 in book 1 of the Elements. Still, mathematicians are also humans and in fact try in many ways to overcome impossibilities in various ways. The most well-known way to do it is to use ideal elements. Nicholas talked about those yesterday. I'm going to take my examples here from Wallace's Arithmetica Infinitorum, where he says, well, since if we're just having the natural numbers, we can't subtract 5 from 3, so we invent the negative numbers as sort of ideal elements. We still cannot divide 5 by 3, well, then we invent the rational numbers. We cannot extract the square root of 2, well, then we invent the irrational numbers. So we can invent these ideal elements to get out of impossibilities. However, it's not only this way that mathematicians have tried to get out of impossibilities. And let me mention probably the first proof of impossibility in the history of mathematics, namely in connection with the problem of finding the greatest common measure of two line segments. This very fundamental problem in Pythagorean mathematics, where they wanted to show that everything in the world can be described by ratios of natural numbers. And here we find both the solution, but also an impossibility result mentioned in Euclid's Elements. In the theorem 10.2, he proves the impossibility result, namely that if the Euclidean algorithm does not end after a finite number of steps, then the two line segments are incommensurable. That is, there doesn't exist any common measure at all. But you also have the existence or possibility part, because he shows that if you use the Euclidean algorithm and it ends, then you have found the largest common measure. Now, of course, other cultures have been faced with this problem, although they probably didn't have a proof of the impossibility here, but they came around it by either, where did I put that? Anyway, by either approximating the numbers here or by introducing new numbers in the style that Wallace also talks about here, ideal numbers. For example, square root of 2 or something like that. Now, it's interesting to see that we don't know, actually, which are the two first line segments that were proven to be incommensurable in Greek mathematics. One suggestion has been that it could be the side and the diagonal in this holy symbol of the Pythagoreans, namely the pentagram. Indeed, if we take the diagonal of the regular pentagon and compare it to the side of the pentagon, then after 2 steps in the Euclidean algorithm, you're actually left with the side and the diagonal in this smaller pentagon. And of course, after another step, you're left with the side and diagonal in this one. And so obviously this Euclidean algorithm doesn't end, and therefore these two quantities are incommensurable. It's also worth remarking that Euclid does not provide any such proof of two actual line segments, side and diagonal in a square or a pentagon or something like that, that are incommensurable. And apparently have thought that these kind of results didn't quite fit into the Elements. Although they are, of course, very important because the discovery of the incommensurability shaped the whole rest of the Greek mathematics. So indeed, what they did was not to invent new numbers, but what they did was to deal with geometric magnitudes without assigning numbers to them. So that is what Zeuthen calls the geometric algebra. And then they invent a theory of proportion that does not use numbers either. Actually, they introduced 2. Theaetetus used the Euclidean algorithm, and Eudoxus produced this wonderful theory of proportion that we find in Euclid Book 5. And this is their way out of this impossibility. And it's, of course, a very singular way out of the impossibility that shaped Western mathematics all the way from the Greeks until, well, sometimes in the 17th century. Here we have a very important example of how mathematicians got around an impossibility in a very fundamental way. Now let me mention another case where existence and impossibility gets close together, namely in the classification of mathematical construction problems in Greek times, and especially Pappus, who divided construction problems into three classes: the plane problems that can be solved by ruler and compass, the solid problems that can be solved by using conic sections also, and then the line-like that uses other curves than circle and straight line or conic sections. And according to Pappus, it's a methodological flaw to use a too complicated method to solve a problem. So in order to prove that a certain problem belongs to one of these classes, you have to show that it can be solved by the methods of the class, but you should also prove that it cannot be solved by using a simpler construction. So for example, in connection with the trisection of the angle, Pappus claims that the trisection and the cube duplication also, they are solid problems. And he actually proves that they can be solved by conic sections, intersection of conic sections. So that's the existence part. But then when he wants to say that they cannot be solved by ruler and compass, which he also needs to say in order to show that they are solid, then he doesn't come up with a proof. And actually he thinks that it's actually ridiculous to try and find such a solution. He ridicules other mathematicians who try. So in a certain way, he seems to think that this is not a mathematical result in a certain way that needs a mathematical proof. It seems to me that he thinks of it as a kind of meta-mathematical result about mathematics, but not as a mathematical result that it is impossible to construct them with ruler and compass. Yeah. The first one, I think, who quite very clearly said that the impossibility of proving, say, the trisection of the angle can be done by ruler and compass, that is a mathematical result and must be proved by mathematical means, is Descartes, and he actually gives a proof. The proof is not correct, even with the standard of the day. And one reason is that he doesn't have the correct algebraic translation of what it means to construct with ruler and compass. Instead, he sort of uses this idea that in order to construct a problem, you have to intersect two algebraic curves that Norbert talked about yesterday. He quoted Euler for this result, this idea. And that, of course, is not in harmony with what you do when you solve things with ruler and compass, because there you make a whole sort of system of intersections of straight lines and circles, not just one intersection. And also for that reason, Montuclat tries to upgrade Descartes' proof, but it is equally wrong. So the first one who really could prove such an impossibility result was Gauss, who translated what it means to construct by ruler and compass into an algebraic thing, and then could prove that certain regular n-gons can be constructed with ruler and compass. Now that is the existent part. He also claimed that he could prove that other n-gons cannot be constructed with ruler and compass. But he says, well, too bad, my book is already too long and I'm not going to present the proof here. So although he thought it was a mathematical result, he didn't think apparently that it was as important as the existence result. Yeah, let's keep that in mind. That's it. And the first actually who then did the impossibility result was Van Zel, whose proof is not entirely correct. Hartshorne has proven that there is a mistake, and that was actually then repaired by the Dane Julius Petersen, whose proof became most famous through the publication in Felix Klein's little book about geometric constructions. Now, let's go to a...
Does that thing use Galois theory explicitly? I mean, does it refer to Galois?
No. No, you don't need, I mean, you don't need the whole machinery of Galois theory. You can talk of pre-Galois theory, somebody talking about, but you don't need the Galois theory. He uses some results that are similar to Abel's, but not Galois theory.
But was Galois not sufficiently known, say,
Excuse me. Could you
No.
save your question till the end?
I mean, Galois lived 30 years after Gauss, so he was certainly not known to Gauss. No. So let me turn to another place where existence and impossibility come together, namely in the question of diarisms. Now, Ivan talked about this yesterday. He took some examples from Diophantus. Here I'm taking some examples from Euclid. And in this case, in Euclid's case, the diarisms are both necessary and sufficient. We discussed that yesterday. Here they are both necessary and sufficient. And let's take the simplest example that is, well, in some sense simplest, namely Euclid's proposition 122, which is to construct a triangle out of 3 straight lines which equal 3 given straight lines. Then it follows also after this that you have a diarism here. Namely, thus it is necessary that the sum of 2 of the straight lines should be greater than the remaining one. And in this case, this is a triangular inequality, right? And he has actually 2 theorems about this. In the 120, he proves the triangular inequality in any triangle. So it says that if these 3 lines do not satisfy the triangular inequality, you cannot construct the triangle. And then in 122, he proves by the construction how to solve this problem if the diarism is fulfilled. So, and that proof is quite simple. I mean, it's obvious what he does. He takes the 1 line segment, puts it here. Then he draws a circle with this center and the 2nd line segment and the radius. Then one with this center and the 3rd radius as its center. And where they intersect, he takes the intersection points and connect it up to these 2. And here we have the triangle. Now, of course, the question is whether that point exists at all. And that, of course, where we should use the diarism. But the funny thing is that Euclid doesn't mention the diarism at all, and he doesn't mention why this point exists here. And traditionally, historians of mathematics, mathematicians, have considered this a flaw of Euclid and have tried to sort of repair it by adding certain axioms, yeah, to the Euclidean axiom system, so that you can actually conclude that there is an intersection point here. Now, the more modern way to deal with this is to look at sort of diagrammatic reasoning in mathematics. That's something that many modern historians of mathematics do, discuss how you can, from diagrams, you can sort of get results in mathematics. And also in connection with Euclid, this has been discussed. Instead of saying Euclid has made a mistake, they say, well, let's investigate what kind of arguments do Euclid actually base on diagrammatic reasoning. Let me just mention that Ken Manders and Vincenzo De Risi has both written some very interesting work on such diagrammatic reasoning in Euclid's Elements. Right. Well, as another example of a diarism, let me mention the elliptic application of areas. See, this is Euclid's book 628, And I'm not going to read it, because even if I read it and you didn't know it, you wouldn't understand what I said. It's a very complicated statement, so I'm going to deal with it only in a special case, and actually let me not read it, but let me do what I'm sure Euclid did when he had his students. He would draw things. So here we have a line segment given, and we have given also a polygon with a certain size, C. And then the problem is to construct a rectangle lying along this given line here, such that its area is equal to the area of this given polygon, C, and such that out here there's missing a figure here which is a square. So we could say algebraically, what can we translate this into? If we call this side of the rectangle x and this one y, then we want the area C, x times y, to be equal to C. And since this is going to be a square, then this line segment is equal to that one, which means that x plus y is equal to b. So actually this corresponds to the solution of these two equations here. How then does Euclid solve it? Well, he starts out by drawing here the square on half of b. So we draw this square. And then he draws a little square here, which is equal to the square on half of b minus c. So he's trying to draw this here, and which means that the rest out here is equal to c. And then he completes this rectangle here, and that will actually give him the solution. Oh, sorry. That will give him the solution, and why is that? Well, because since it's easy to show that this gnomon here, which was c, is equal to the area of this rectangle. So that means that this is fulfilled. And secondly, it's easy to see that this is a square, because the big thing here was a square, and this little thing is a square, therefore that is also a square. So we have solved the problem, and you could say, and algebraically, what we have done is we have constructed this square, which was in area equal to the square of b half minus c. Then if we take the side of that square, that's equal to the square root. And if we add it to b half, then we get x. And if we subtract it from b half, then we get y. So this is the solution in algebraic terms of this. Of course, here we need to use the diarism, and Euclid says that this is only possible if the given area is less than the square on half of the given segment. So only if c is less than b half squared, which means that the square root is real. And he actually proves, in this, he proves that you can, if this is satisfied, then you, of course, you can draw this square. Otherwise, you can't draw the square here. So you need it. And you also show that if you have a situation like this, then the largest rectangle you can get here is the square on b half. So therefore, it cannot be larger. So he proves both the impossibility part and the possibility part here. We find something similar in algorithm. Indeed, if we eliminate y from these two equations, we get this quadratic equation. And about that, algorithm says that if b half squared is smaller than c, then the example is impossible. So if the discriminant is less than 0, the example is impossible. And indeed, there are other Arabic mathematicians who study impossibility results like this, especially as Samabal, Rushdie Rashid has studied these in some of his writings. But I think the most, should I say, impressive Arabic discussion in this direction is by Sharaf al-Din al-Tusi, who looks at cubic equations and shows how many solutions there are for any cubic equation. And So he looks at various types of cubic equation. Let's just look at this particular one here and see how he deals with that. In fact, he then interchanges these two sides here, so we get this expression here instead. And then he deals with this left-hand side here as a kind of function of x. It's actually more or less the first time that we see a function concept in the history of mathematics. If we draw this, the curve corresponding to this function, it looks like this. And we're only interested in the positive. He doesn't draw this curve, doesn't draw the graph. But he argues that, for x positive, of course, this will look somehow like this and will have a maximum somewhere. And he then, with very ingenious methods, calculates where this maximum is. It's at 2b over 3. And the value of the maximum is then 4b cubed over 27. And which means that if this d here is larger than that value, then there are no solutions. If it's equal to that, then there's one solution, and if it's smaller than, there are two solutions. We are, of course, only talking about positive solutions here. So he has actually dealt with how many solutions are there depending on the value of d. And both dealt with the I should say that also the existence then is, he proves that in the case here and the case here, he can construct the solution by intersection of conic sections. So this is a fantastic piece of mathematics, and Rushdie Rashid has tried to argue that Althussi actually invented the calculus in this connection with finding this maximum here. This has been rejected by Jan Hogendijk later on. Okay. Let me just go back to the elliptic application of areas, or to Cardano, who says we want to divide 10 into two numbers such that the product is 40. Now, of course, he knew very well that this is impossible. Indeed, as he knew from Euclid or from Al-Khwarizmi, that since half of 10 is 5, and 5 squared is 25, well, 25 is not larger than 40. And for that reason, there is no solution here. But he still writes down the solution. He writes these complex numbers here as a solution. And it's interesting to see how he deals with this problem. Here we have this page where it happens. So actually, he starts out with this geometric figure, and he begins the Euclidean construction. He begins to draw the square on half of this line. But then, of course, he has now to insert a little square here, which is equal in area to 25 minus 40. That is, in area, it should be minus 15. Well, that's hard to write, to just draw such a square. So he actually just stops the geometric construction at this point, and then just continues with arithmetic or algebraic notation. And he has a notation which allows him to write the radix, the square root of minus 15. So here we have the solution 5 plus square root of minus 15 and 5 minus the square root of minus 15. And this is, I think, a very interesting example where the notation plays a very important role for what he can do. I mean, so he invents these ideal numbers, you could say, the complex numbers, but he couldn't only do it in connection with this new notation for the square root. And often we think of the geometric and the algebraic version of this as being sort of equivalent. But here we see that they are not equivalent in practice, because the geometric way of looking at this problem doesn't allow you to make this leap to the complex numbers, but the algebraic one does. And so it's a very interesting example where you can say that notation is used as a cognitive artifact, allowing you to make these new ideal numbers. Yeah. That out job. Now let me turn to another example where it's quite interesting that the same piece of mathematics by some were considered to be a proof of existence, and by others were considered to be proof of non-existence or impossibility. And here I'm talking about the proof of the parallel postulate. It's well known that Euclid formulated this postulate, and ever since Euclid, many people have tried to prove it from the other postulates, but about 1820, Gauss, Lobachevsky, and Bolyai all came to the conclusion that one probably cannot find such a proof of the parallel postulate from the others. So instead, they constructed a non-Euclidean geometry based on the negation of the parallel postulate. Still, they had no proof of consistency of this new domain, but that came out of a very nice observation made by Beltrami, who discovered that if you look at a surface with constant negative Gauss curvature and considers geodesics on such a surface as lines, then the geometry on such a surface is non-Euclidean. Now today, we follow Poincaré, saying that this shows that the non-Euclidean geometry is just as consistent as Euclidean geometry, because if there were an inconsistency in non-Euclidean geometry, it would turn up in the model, as we call it today, in the model in the Euclidean geometry. However, this argument using models were apparently so novel at this time that Beltrami himself didn't draw this conclusion. It was only when Well pointed it out to him that that was what he had proven, that he said, oh yeah, maybe that's what I had proven. And what's also interesting is that, yeah, do I need the next slide? No. That some philosophers interpreted the proof differently. They said, well, no, what Beltrami has shown is that there is no non-Euclidean geometry. Because in fact, what Gauss, Lobachevsky, and Bolyai thought was a new kind of geometry turns out only to be the geometry of geodesics on a surface with constant negative curvature in Euclidean space. So the only thing we have is Euclidean space. We don't need, there's nothing like non-Euclidean geometry. That's, I think, quite interesting that you can interpret things so differently. Well, talking about possibility and impossibility and their relation, it's almost impossible to skip this wonderful Diophantine equation here, where you ask for solutions in natural numbers a, b, c, and n for this equation here, where n equal to 1 is trivial. N equal to 2 was solved completely by Euclid, who found out how to find all such solutions. I'm not going to go into it too much. But he could, for n equal to 2, he could give all the solutions, the so-called Pythagorean triples, that were actually, at least some of them, known even to Babylonian mathematicians. And at least Neugebauer tried to argue that showed that they had the same understanding as Euclid of these numbers. That has been debated since then. But that is the possibility part of this. Well, of course, there's an impossibility part formulated by Fermat, that for n larger than or equal to 3, there are no solutions, and that was proved, as we all know, by Andrew Wiles. Now, what I want to say in this connection is that here we have the first example that I've mentioned of an impossibility theorem that became more famous than the corresponding existence theorem. I mean, who remembers Euclid's results? But we all remember Fermat-Wiles results. And of course, it's partly because, of course, the Fermat result is much deeper and much more difficult. But it's also because there was a change of, of evaluation of impossibility results. We've seen that earlier, people had thought of impossibility results as meta results about mathematics, or as not very interesting problems in mathematics, at least not as important as constructive existence proofs. But now we come to let me mention one more example here where the impossibility result has become much more famous than the possibility result, namely in connection with voting methods, or social choice theory, as it's also called. Here, Duncan Black, who was a Scottish mathematician, came with some positive results around 1950. He's not very famous, and actually I haven't been able to find a picture of him even. And almost simultaneously, the American mathematician Kenneth Arrow proved his impossibility result that has become extremely famous. They both had degrees in both mathematics and economics, which was not so usual at the time, I should say. Now let's have a look at the problem. The problem they faced is the problem of how to conduct an election if there are more than two candidates. Here, Condorcet had already sort of thought about that in a book, famous book of 1785. And at first he had pointed out that majority voting or plurality voting is not always a good way to elect a candidate for something, president or whatever. In fact, here we have an example. It's a little simpler than his own example, but never mind. We have 6 voters, 1 to 6, and then we have 6 candidates here. And then we ask each of the voters to organize, to what's it called? Rank, thank you. Rank the different candidates. And the first voter, he ranks A on top, and then next B, and so on, and he dislikes F the most, and so on for all the. So let's just say that's how they rank them. So if we make now a just plurality vote, when of course then A will win, because there are 2 people voting for A. B, C, D, and E, they will get each 1 vote, and F will get 0 votes. So A will be the winner. But unfortunately, A is also the most hated of all the candidates, right? These 4, they dislike A the most. So as Condorcet says, it's probably not a good idea to elect A. So what should we do? Well, Condorcet suggests that the correct winner should be the one who wins by majority over each of the other candidates if we make pairwise votings. So let's look again at the same rankings here. In that case, B will actually win. Why is that? Well, if we look at a vote between A and B, then A will have these 2 votes, but B will have all the other votes. So he will win over A. And similarly, if we conduct a vote between B and any of the other ones, B will also win over them. So B is what we call the Condorcet winner. The bad news is, unfortunately, that there need not be a Condorcet winner. Indeed, if we look at this very simple example here, we have 3 voters, 3 candidates, and the first voter ranks them A, B, C, the next one cycles it, so we get B, C, A, and the third again says C over A over B. Now, if we conduct an election between A and B, then let's see, A will get that vote and this one vote. B will get this vote. But A will win over B with will beat B 2-1, right? What about B and C? So B is above C here and here. So B will get 2 votes and C will only get 1 vote. So A beats B and B will beat C. So you would imagine that A will beat C, but no, it doesn't happen. See here, we have in a vote between C and A will have this vote, but these 2 will go to C. So actually C will beat A 2-1, which means that the combination is intransitive, or inconsistent as they sometimes call it, namely A will beat B, who will beat C, who will beat A. Which means that whoever you elect, there will be another candidate who will beat that one in a pairwise election, which is very bad news for sort of our usual way of thinking about democracy. And the problem here is often called the Condorcet paradox. So how do we do then? In fact, let me start with Duncan Black, who had a new way of illustrating people's preferences. He didn't know about the Condorcet paradox in the beginning when he invented this graphical notation. So he said for each, let's rank, just put the candidates here on an x-axis here. So these are the candidates you can vote for. And for each voter then, you make a graph. So let's look at the blue graph here. It's one particular voter's preferences. And he actually prefers D the most, then E, then F, then C, and so on, like that. So these curves tell us how his preferences are. Now let's look at another. Here we have the preferences of another voter, and here of a third voter. And then Black showed that if all the voters have what they call single-peaked preference curves, so a curve which has a peak from where they go down in both directions. If that's the case, then the Condorcet winner will be the point in the middle here. So that will be the one which has equally many tops to the right and to the left here, so the median. Which is a nice way to show how to find the Condorcet winner. And he published this as a result. But then he discovered that it is not always possible to rank these such that all the preference curves here are single-peaked. That is the same as the Condorcet paradox. And he says that when he discovered it, my stomach revolted in something akin to physical sickness. So actually he, for various reasons I don't have the time to go into it, didn't publish much more than this. Now let's look at the other person, namely Arrow. He came to the problem from, what should I say, welfare economics. So his idea, we have a population of n people, and we ask each of them to rank the possible social states in this society according to their likeness. And that will produce various orderings. So the first person has a ranking, which we call R1. The second has another ranking, and so on. So we have n individual rankings. We can also think of it as n ballots for a vote. And then he wants to find a social welfare function which out of these individual rankings constructs a societal preference ordering. So what society should think of as the preference ordering. And that he calls the welfare function. We could also say it's the voting method. Now, in order to talk about these rankings, he simply uses the modern, then very modern idea of an axiomatic theory of ordered sets that he knew because he had followed lectures by Tarski on this. And yeah, now earlier people who have thought about voting methods, and there were many, had done like this. They had sort of cooked up a voting procedure that they thought looked promising, and then they had derived its properties. And usually they had always found out that it had some properties which were not very desirable. But Arrow said, no, let's do it in the modern axiomatic way. Let's start out with formulating some actions that we want this welfare function or the voting methods to satisfy, and then try to find out what we can say about the voting procedure or welfare function that satisfies these properties. And so he formulated 5 very simple, very innocent-looking conditions that everybody, I think, who's thinking about how to construct an election in a democracy, they should satisfy. And then began to find out what can we say about the voting procedure satisfying these properties, and it turned out that you could say that they don't exist. There is simply no voting procedure satisfying even very weak axioms about what such a procedure should do. And he says about his so-called general possibility theorem here that theorem 2 shows that if no prior assumptions are made about the nature of individual orderings, there is no method of voting which will remove the paradox of voting discussed in chapter 1. That's the Condorcet paradox. Neither plurality voting nor any scheme of proportional representation, no matter how complicated. Similarly, market mechanism doesn't create a rational social choice. So this is a very depressing conclusion, but it earned him the Nobel Memorial Prize in Economics in 1972. Whereas Black's results, well, they were more or less forgotten. So you can say, when did impossibility theorems receive sort of status as real good theorems in mathematics? Well, I think it happened in the 19th century. And let me just point out that around 1830, many new impossibility theorems were formulated and proved. Abel proved that it's impossible to solve the general quintic by radicals. Liouville proved that certain integrals cannot be written in finite forms, and certain differential equations cannot be solved by quadrature. Vancel proved a lot of impossibilities. I have mentioned several of them. But it was still a young man's game, and we have to go up to about 1870, 80 or so until impossibility theorems got full citizenship in mathematics. And in order to substantiate that, let me quote Hilbert, who says in his famous talk about mathematische Probleme in 1900, that in recent mathematics, the question as to the impossibility of certain solutions play a preeminent role. So that's in recent mathematics, right? And he mentioned here the proof of the parallel postulate, the quadrature of the circle, and the solution of the quintic, and said that they have finally found fully satisfactory and rigorous solutions, although in another sense than that originally intended. Of course, it was intended that you find the solution. Well, what you did was to prove that there is no solution, that they are impossible. And in that connection, he sort of said, well, we should include an impossibility result as a solution of the problem, because in this way, all problems will have solutions. Abel had said something similar in 1829, and he calls this an axiom of the solvability of every problem, saying that either you can find the solution or you can prove that it's impossible. And he says about this, that this conviction of the solvability of every mathematical problem is a powerful incentive to the worker. We hear within us the perpetual call, there is the problem, seek its solution. You can find it by pure reason, for in mathematics there is no ignorabimus. Now, of course, by formulating this strong idea about impossibility results, ironically, he missed the next major impossibility result, namely the result due to Church and Turing and Gödel, who proved that, in fact, in a sufficiently strong axiomatic system, it is in fact possible to formulate theorems that cannot be proven, theorems that cannot be, problems that cannot be solved, but you cannot either prove that they are unsolvable. And so when Hilbert, in a similar famous talk in 1930, says, wir müssen wissen, wir werden wissen, Turing and Gödel, and Church says, no, that's wrong. If we talk about existence theorems, there's a similar story. Also, they, as far as they were not constructive, were not considered so important until we get into the 19th century, where we find a lot of such non-constructive or more or less constructive existence arguments. For example, Cauchy, in connection with infinite series, have convergence tests that doesn't point out what the sum is, but says there is a sum of a series, and so on. And we have the Dirichlet principle, Hilbert's finite basis theorem, and so So we begin to have these kind of non-constructive existence theorems. We can say as a whole, this is a special case of a tendency towards more conceptual mathematics and away from more calculatory and formula-based mathematics. Now, in the beginning of my talk, I tried by flashing some title pages to argue, at least say that this study of impossibility results is a kind of modern history of mathematics. But let me just end up by mentioning a few of the things that I have mentioned in my talk, which certainly are modern. Well, first of all, of course, I've been dealing with various theorems, Fermat's theorems, Gödel's theorems, Arrow's theorem, that are all theorems from the 20th century. And of course, that is, I suppose, by nature, modern history of mathematics. But I've also mentioned various modeling techniques, especially Arrow's way of modeling social behavior using only the axioms of ordered sets. And of course, you can continue to study a lot of other mathematical models also in economics, which is certainly also a modern idea in the history of mathematics. Tina has told more about some other examples in the beginning of this workshop. But I've also looked at, I've also mentioned impossibility results in Arab texts. Arab texts are beginning to be studied very much, and we find a lot of new interesting things in those, and that, of course, is also, you can call that modern. But also I mentioned this approach to well-studied mathematics, even ancient Greek mathematics that perhaps we thought we have studied to death. But in fact, there are these diagrammatic arguments in Euclid is discussed in a completely new way nowadays. And similarly, I also talked about something in the same vein, namely studying notation as a kind of cognitive artifact that's also dealt with by philosophers and mathematicians, historians recently. So I will end here. I think that it's obvious that there are lots of things to go on with when we look ahead. We see a lot of new areas where we can enter, and it is not over, even if here we have the solution of the quadrature of the circle. You see the angels up here, they square the circle. Oh, actually, it's actually, maybe it's the circle that's being squared, or the square that's being circulated. Anyway. Yeah, thank you.
Thank you. We have time for questions.
Question about Duncan.
Black. Yeah.
Perhaps if we could go back to the slide on the failed attempt by Duncan. Is that the name? What happens in the case? You said that the solution was the one in the middle, but what if you have an even number of members?
Yeah, then there will be two who will get the same amount, and then there is no way to. Yeah, and then also, the ordering, for example, that Arrow uses also allows two different things to be equal on the same level. So you can also, with him, you can also have things to. But then the question is how to solve that question, and that's of course that is unsolvable by. You just have to draw the lot, I suppose. Yeah, but this result was also found by Arrow, and he didn't know that it was found by Black, but then found it in a journal, and Arrow gave up studying this problem several times. Once was when he discovered the Condorcet paradox, and he also says that it made him sick or something like that. It was a very problematic discovery for him, so he put it aside. Then he discovered this result, and then found out that Black had already proved it. And then then the third time, when he became interested in sort of game theory and the question about whether, when you talk about games between people, that's one thing, but if you talk about games between nations, can we say that the nations have a priority list? How does that work? And then he thought about it again and found out, well, in a certain sense, no. A nation cannot have a rational ranking in a certain sense. And then he sent it in. Oh yeah, I should also mention now, you have no other questions, that then Arrow wrote this down as in a paper and sent it to Econometrica, whose editor then sat on it for, no, that's wrong. It was Black sent his result into Econometrica, who then sat on it for 1.5 years and then said, if you rewrite your paper in such a way that you take account of Arrow's ideas, then you can publish it. And he became very angry because actually he had found them before Arrow. And it turned out that the editor of Econometrica was the supervisor of Arrow. So it was a nasty situation. That also explains why Black just didn't publish anymore.
Do you think it partially also explains the obscurity isn't just due to it being a positive result? Yeah. No, I mean, if you had solved the problem, then it would have been wonderful. But well, you can't. Well, of course, you can always tingle with these requirements. But there's a whole industry of then rephrasing these conditions that Arrow had into seemingly weaker conditions. But you have to weaken them very much in order to get a solution to the problem. And so even if you change them quite a lot, you will still get impossibility results. And there's a whole industry of Arrow kind of impossibility results. If you look at the internet and Google impossibility results, then Arrows come up as the first one. It has most quotes. And of course, it's also because it's the only impossibility results that's called impossibility result. But you may have noticed that he himself in the beginning called it a possibility result. I don't know if you noticed that. He calls it himself the possibility, the general possibility result. And that was because Koopmans, who was also at this place where he was working, he hated the idea that something was impossible. And therefore he said, you cannot call it an impossibility theorem. And so to please Koopmans, Arrow in the beginning called it my possibility theorem. But then gradually everybody else began to call it impossibility theorem, and he himself also began to call it that. It is quite a striking result. The claims are apparently innocuous, and then it turns out you can't do it.
Yeah, it's very sad.
Any final questions? Yeah, go ahead.
I was wondering, you looked at, when you were talking about new approaches at the very end there, you mentioned diagrammatic methods in Euclid. And the example you did was kind of clear, but how do you identify diagrammatic methods in Euclid?
Well, there are certain things where like here, it's also, I mean, the very first proposition is a simpler version of this one. It's the construction of the equilateral triangle, which is the first you meet. And of course, you have the similar problem. It's problems where you somehow assume something that is not a consequence of any of the postulates. And where Hilbert, I mean, somewhere, I mean, where Hilbert had to repair it to get the full list. And so these people, they separate, they make a distinction between propositional arguments. That is the one that are based on the propositions and the actions, the formulated actions. And then something that apparently Euclid thought you could somehow deduce from just the picture. And this of course doesn't imply that you cannot deduce the length of a line segment. That's something you will have to find out, I mean, as long as you can talk about length. But there are things that apparently he thinks you can do by just looking at the figure. And I mean, the modern way to think of this is not that he made a mistake, but that he had somehow the idea that you can look at it. And of course, in a certain sense, it's trivial, but if you begin to argue about it, then there are certain, you have to distinguish between, is this the longest one and these two the shortest ones and so on. There are all kinds of cases here, and it becomes messy if you really want to make this argument here. And of course, there are two different questions in a certain sense. This one is, do they cross? And the other question is there a point where this crossing takes place? They can be distinguished, one being sort of the completeness of the line or the circle, and the other one being something about lying on one side and the other side kind of actions. But yeah, I'm not an expert in this, but I know it's quite interesting, and it's a part of a discussion, wider discussion about how mathematicians use diagrams in their reasoning, and that also includes modern mathematics, the stuff they do up there on the blackboards all the time.
All right, we'll thank our speaker again.